My name is Grace and I'm here with Kate, and we're going to be presenting to you today all about reacting to an event-driven world.
So to get started, let's all get some coffee. I think that the time zone, if you're in the time zone of the event, then this is a good time to be getting coffee. Here in the UK, it's quite late in the day, so great to get coffee to stay awake. We have plenty of coffee demos out there. A lot of people, when they start to look at new systems, that's where they start with some basic demo that they can look at to understand how can they improve their system. And we have a lot of people who will start off with breaking down applications into microservices and using HTTP and REST-based APIs as their main methods of communication. But if you build a system like this, where you have coffee lovers coming into your coffee shop, putting in a HTTP request to the coffee shop to place their order, and then that being forwarded on to a barista, you quickly find that if you have a lot of coffee lovers, you're going to get a bottleneck at the coffee shop. The coffee lovers have to stand around and wait for the response from the coffee shop while the barista is still making their coffee. So this isn't a very efficient way to do things. And a good way to start making improvements to the system is to look to event-driven architecture. So the idea behind event-driven architecture is you have this event-driven messaging backbone, you've got microservices that are publishing different messages into the backbone, and then other ones that are consuming. And if we add this into our example, then kind of helps us. We can see immediately, okay, we maybe don't have a bottleneck anymore. We've got this great event backbone with lots of events that are on our orders and our queue topics. And this allows the barista to have some decoupling from the coffee shop. And if you actually run the two versions of this example, you will see that with a lot of coffee lovers, the second example works much better. So this code is all on GitHub. You can actually go and try it out. But there's plenty of examples that are similar to this, where we take HTTP and put in an event backbone and everything is better. So because of this, it's really tempting to ask this question, which is your coffee shop non-blocking and highly responsive? Well, the question is actually, is your microservice system non-blocking and highly responsive? And to go, well, I'm using Kafka, so of course it is. But that's not quite the whole story, is it, Grace?
Unfortunately not. And as a lot of you here will know, as we're at sort of Reactive Summit, this is sort of where we need to be considering the characteristics and the behaviors of reactivity on top of useful tools like Kafka. Kafka is not the end result. Unfortunately, it's just a useful tool to use. So what we really need to be considering is how we build these non-blocking, asynchronous, highly reactive and responsive applications and systems as a whole. So let's take a look at that barista example again and take a look at some of the issues we might come across just by sort of shoving in this event backbone and this event-driven architecture and assuming it solves all of our sort of blocking and potential points of contention. So one potential problem is in this diagram, we only have 3 coffee lovers. But what if we had lots more? There are many, many, many more coffee lovers in the world. So what happens when our coffee lovers, we suddenly get a bombardment of coffee lovers and they're all trying to order coffee? Well, more coffee lovers obviously results in more coffee orders. And although we have our event backbone, we still have a potential point of contention here, because although our coffee lovers don't have to wait at the till for each coffee order to be processed one by one before the next person can be served, we do have that sort of asynchronicity in allowing this event backbone and having that queue and adding our orders to that queue or that topic. But our point of contention here is our single barista microservice. So we only have one barista here to make all of these coffee orders. And as quick as they might be as a barista, it's going to take some time to get through all those coffee orders. So here you can see where just shoving in an event backbone doesn't necessarily make our application non-blocking and highly responsive and reactive. Another potential point of contention, another potential issue we might come across is what happens if a downstream component, that could be maybe an additional microservice doing some sort of processing on the data, or maybe a third-party database or third-party application. What happens if that third-party component or that downstream component goes down, gets stuck in a process, or becomes sort of blocked up, essentially? So in this case, we've added an extra component to our diagram. This is the serving table. So now our barista has to put the coffees down on the serving table for our coffee lovers to be able to come and pick them up. But what happens if our coffee lovers are being a little bit lazy? They're not coming to pick up their coffee. And so now we have a pile up on the table. So now our barista is juggling coffee, trying to get their next order made, but they've got no hands free because they can't put cups down on the table. So in this case, it's sort of representing that service going down, our barista being stuck because it can't pass those orders on, and a potential point of sort of contention, a potential bottleneck, and a potential point of failure has occurred here. And because we haven't implemented some of the key characteristics we need in reactive systems, we haven't made a completely reactive and responsive application. So what we really need to be doing is sort of thinking about the various different cornerstones of the Reactive Manifesto. And that's why it's so important not just to assume that you can shove in this event-driven backbone or this message-driven backbone or event-driven architecture and expect it to be magically responsive all the time and sort of reactive. And that's why we need to consider things like elasticity, so scaling our resources up and down depending on the load to our system. We need to think about resiliency. So have we inbuilt resilient behaviors in the face of potential failures? And is our application as responsive as possible to these potential sort of events and state changes within our system? So how do we go about sort of building in these characteristics and really building completely and holistically reactive systems with Kafka as a tool for that? Let's take a look at a fairly simplistic application. So this application only has sort of 3 microservices, just because we're showing this as a demo to look at the various layers we need to be considering. We've already mentioned the data layer. So the fact that we're using Kafka helps us to decouple components of our application and enable more asynchronicity, as we showed in the Barista example. But as we also showed in the Barista example, there are other layers we need to think about. And that includes sort of how the various components of our application communicate with each other, communicate with Kafka, and interact together as a system. And that's where we can really utilize reactive architecture patterns. So we've got sort of a list of 4 of some of the more common patterns Kate and I have come across. There are lots of other patterns out there if you want to take a look at them. But essentially, these are some of the more common ones. And the one that Kafka can really help with in terms of providing this sort of almost like a buffer in between the components of our application is back pressure. So actually, by utilizing Kafka, we can implement some of these design patterns and some of the reactive frameworks and toolkits that connect with Kafka that we can utilize when building and designing our applications also enable this all-important back pressure in their communication with Kafka and other components. So these are some really useful design patterns, and you can Google more if you're interested in finding out what other design patterns you can put into use at the system level. So we've looked at the system level. Let's take it one step sort of further down, deeper. We also need to be looking at inside our microservices. So is the logic within our microservices also reactive and non-blocking? So we can do that by implementing things like reactive programming patterns. And that can include futures. So if you're a Java developer, for example, you're probably familiar with this concept. And that can also include reactive programming libraries, like, for example, RxJava, Small Mutiny. There's just some examples. And the reactive frameworks we'll go on to later utilize these programming libraries quite a bit. And we've also got things like the reactive stream specification. So this specification was a community-driven specification, providing a standard for handling asynchronous data streams while providing that all-important back pressure that I mentioned. So we can see here that there are various different layers we need to be considering alongside their interaction with Kafka. So how do we go about configuring Kafka so that we can have a really truly responsive reactive system?
So many people are starting to use Kafka in their reactive systems, but how can we make the best of configuring it? First, we need to understand what Kafka is. It's an open source distributed streaming platform, but it does work differently from other traditional messaging systems that you might have already come across. And one of the key parts of this is it provides stream history. So in Kafka, you can have events that can be persisted and reread by consumers later on. All of the data is immutable, so messages shouldn't be altered as they flow through Kafka. And it's really built to have designed into it high availability, scalability, and the capability to have very scalable consumption. So it's really designed to have a high throughput and lots of consumers consuming all of the events. So how do we take Kafka and make sure that we've configured it to fit with some of those aspects of the Reactive Manifesto? because Kafka as a technology is so popular because it is so configurable. It's designed for many different use cases, but that does mean that you need to think about how you're going to configure it with your reactive systems. So let's start by looking at message-driven. In the Reactive Manifesto, it defines that all of the things that flow through the system should be messages, and the system as a whole should be message-driven. Well, in Kafka, the things that we pass through the system are called records. The great thing about Kafka is it doesn't have any strict definitions around the format of the data you flow through it. To Kafka, everything is just a record. You can publish and subscribe to streams of records, you can store records in a durable way with that stream history, and you can process streams of records as they occur. It's up to you to decide what format those records are going to take, what data type it's going to be, and so you can configure it to be message and have message-driven. Next, let's look at resiliency. So Kafka is a distributed system. Normally you would start with a cluster made up of one or more brokers, but normally you start with about 3. So here we've got 3 brokers across our Kafka cluster, and you'll see why 3 is a good starting point in a minute. But Kafka really is designed with resiliency built in. So all of the records that flow through Kafka are broken down into what's called a topic. So a topic is a grouping of similar kinds of records. It's up to you to decide how you break down records into the different topics. But you might have, for example, in our coffee demo, we have a topic that has all of the orders and then a separate topic that has all of the completed orders with just an updated status for them. Then within a topic in Kafka, you have that broken down into different partitions. And the partitions are used for scalability, which we'll see a little bit later on. So for a particular topic and a particular partition within Kafka, it uses something called replication to provide resiliency. So for a specific topic and a specific partition within that topic, Kafka will have one broker which is elected as the leader. All of the other brokers are then called followers. What this means is all clients that want to send records into Kafka to that topic and read the records back out again, they will only talk to the leader. And automatically, Kafka will copy any records that come to the leader to those followers. This is a configuration option, so you have to define the number of followers that you want when you create your topic. So in this case, I would have picked a replication factor of 3, so I get 1 leader and 2 followers. What this means is because Kafka is automatically replicating my records, if for some reason my broker were to go down, as long as my other 2 brokers are still running, Kafka will just have a leader election, and the second broker here, so broker 2, will become the new leader, and all of the clients will get told to talk to the new leader. So what this means is, as long as you set up your cluster so that your brokers are distributed across different systems, then if one part of your system goes down, you can carry on using Kafka and all of your applications can continue working as normal. So this is the built-in resiliency that Kafka has as part of its brokers. And you can see that in case you want to take things down for maintenance, say if you want to update your brokers with new configuration that isn't dynamic, it's great to have 3 brokers to start off with, and then you'll always make sure you've got 1 replica left. So how do we configure producers and consumers that are talking to Kafka with resiliency in mind? Well, here we need to think about resiliency in terms of guarantees of a record delivery. So when I'm sending messages as records through Kafka, I need to think about how certain do I want to be that those records will arrive? Do I want at most once guaranteed, at least once? Kafka does provide some exactly once guarantees, but it's designed for certain types of Kafka applications. So in general, most people look at most or at least once. To achieve this, when you're configuring a Kafka application that's a producer, you need to configure your ACKs and your retries. So ACKs is short for acknowledgements. This setting defines how long a producer will wait to make sure that a record has really arrived into Kafka. And there are 3 different options. You can do a fire and forget, so you don't want to know for certain that it's got through. This is great for if you've got sensor data and if one record gets lost, it doesn't really matter. You can look at a setting of 1. So this means you're just waiting for the leader to receive the record, or you can set it to AX all. AX all means you're waiting for all of that replication to happen before the producer gets told that the message has been received. So you need to consider, do you want to make sure that the messages arrive, but you don't mind having a slightly slower throughput? Or do you want to get high throughput and it doesn't matter if a couple of messages get dropped? Then on top of this, you need to configure your retries. By default, most producer clients have retries turned on and they'll have a certain number of retries that are automatically going to happen, but it's worth having a look at the client that you're using and understanding, will it retry and what will be the effect of that retry? Am I going to get message reordering if something goes wrong? And really drilling into that configuration to understand what's happening. So you can configure your producers to make sure that the records definitely arrive into Kafka. But how do you make sure that applications that are pulling messages from Kafka really do get all of the records that are in there?
So this is where we need to take a look at resilient consumers. So with consumers, as Kate mentioned, Kafka has this stream history. So unlike other sort of more traditional messaging systems, once in those traditional systems, once the record or message has been sort of read by a consumer, it's no longer on that queue. That's not the case for Kafka. So this means that we need to have something called offsets, which are essentially a value assigned to each record on the topic, so we can keep a track of where we've gotten up to consuming. And to do that, we call an API to commit the offset we're up to as a consumer. And there are 2 different ways we can do that. We can either have automatic or manual commits. So let's take a look at the difference in regards to our Barista example and see how some might lead to greater resiliency than others. So in this example, on the left-hand side here, we have a barista. Our barista is representative of a consumer to our Kafka topic. We have our Kafka topic here, and it's got 3 coffee orders on it. So what we're going to do is we're going to take a look at what happens with auto commit. Now, auto commit is essentially, it's where you have no code in your application. So you're relying on the default settings in the underlying client, which is probably, in our case, it was a Java client when we made our own application. And basically what this does is it works on a timer basis. So on a timer basis, it will automatically commit those offsets for the messages that I've read as a consumer from Kafka. So with our barista example here, with the auto commit, our barista is going to start reading from our topic at the first offset. So it's got our coffee order and it's starting to make our coffee order. Because we're on auto commit and we're on a timer basis, after a certain amount of time, our offset's going to be committed. So we've got that tick to show we've committed that. However, our barista's a little clumsy, and whilst producing this coffee, accidentally drops it. This is essentially representative of that microservice going down before we finished processing that record. So now when our barista or our microservice comes back up to reread from our queue, from our topic, it sees that it's already done the coffee order, so it moves straight on to the cappuccino because it's already committed the offset for the coffee. So now our barista makes a cappuccino and then a latte, but unfortunately, when it gets to the end of the topic, it's missed a record. So you can see here that it's not completely resilient by having this auto commit configuration option. So instead, let's take a look at manual commit. So with manual commit, we're actually writing a piece of code to determine when precisely we're going to be committing that offset. So in our example, we're not going to commit the offset until after we finished processing and we've served up the coffee to the board or to the customer. So in this case, our barista starts making the coffee order and it only commits that offset once that coffee order has been served up to the customer. So we only get that tick once we've served it. And now the barista can move on to the cappuccino and then the latte. And now, even if it was to drop the coffee partway through, we wouldn't have committed that offset. And so when the barista comes back up and looks back at the topics, it would know to start at the beginning. So by introducing this small change from auto to manual commit in our consumers, we can really make sure they're as resilient as possible to potentially losing any of those records coming from Kafka.
So we've had a look at resiliency, and we now understand how Kafka provides resiliency built in, but also how we have to understand how our producers and consumers are talking to Kafka to make sure that the records make it all the way through our system. But what about elasticity? How can we scale within Kafka and scale up and down our producers and consumers? So Kafka is built with scalability in mind. It's designed to support big systems with a lot of throughput and a lot of records. So for a particular topic and a particular partition, Kafka will do the replication, as we talked about before, but it also makes sure that for that topic, all of the partitions within the topic are spread out across the different brokers. So here you can see I've got one topic with 3 different partitions, and Kafka will try to spread them out across the different brokers as they're created. This allows us to have scalability in terms of producers, because as we add more producers that are all producing to the same topic, because we have these partitions that are spread across the different brokers, we won't overwhelm just one broker. So this allows a Kafka cluster to handle a lot of records or a lot of messages going to the same topic at the same time. The partitions also come in handy when we look at consuming. Now, in other messaging systems where they're queue-based, when a consumer reads a message off of a queue, it's no longer on the queue for anybody else to read. But in Kafka, that isn't the case because of stream history. And this helps us from a resiliency point of view because it's much easier to reread a message if something goes wrong during processing. But if you want to scale out, you need to make sure that you don't have multiple different consumers all trying to read the same messages. And we do this in Kafka using consumer groups. So a consumer group is a grouping of consumers that will all work together. So let's just look at a quick example. So here I have 2 consumer groups, A and B. The consumers joined the group by, when they started up, giving to Kafka a consumer group ID. As long as they have the same ID, they'll join the same group. And what Kafka will do is it will make sure that between the consumers in a specific group, they will get all of the messages from a specific topic. So what this means in reality is that for group A, where we have 3 consumers, they will get 1 partition each. So my topic only has 3 partitions. Each consumer gets a partition to read from. Ordering guarantees in Kafka are per partition, not per topic. So we don't have any ordering problems here because each consumer is reading its own partition. For consumer group B, there are only 2 consumers. But this works fine because one of the consumers will just read from 2 of the partitions. And Kafka will automatically distribute these different partitions to the consumers and again make sure that between those 2 consumers in that group, they've read all of the messages. But because of that ordering guarantee and because of the stream history, we can't have more than 1 consumer from the same group reading the same partition. So what this means is if you were to add an additional consumer to group A, it wouldn't actually receive any messages. So this means that when you're configuring your Kafka system, you need to think about partitions. You can add partitions as your system is running, but because of the ordering guarantees in Kafka, if you start adding more partitions midway through, some of your records will get moved to different partitions and they won't all be on the same partition you were expecting. So there is a cost to adding more partitions, and the leader election also takes longer if there are more partitions. So when you're setting up your Kafka system for scalability, you need to weigh up these 2 choices and you need to come up with, as best as possible, an estimate of how many partitions you need so that you can always scale up your consumers to the maximum number of partitions and then scale them back down again. So we've now had a look at some of those different aspects of the Reactive Manifesto and how you can configure Kafka to suit your needs. But what about actually writing these clients that are going to be talking to Kafka?
So obviously there is a standard Java Kafka client, and with that comes the standard Java Kafka consumer and the standard Java Kafka producer. And there are some aspects within this, some sort of features that we can utilize, like the pause and resume methods, but these aren't exactly designed for reactive systems. So instead, what we'd suggest is for you to take a look at some of the reactive frameworks and toolkits that are out there that have connectors to Kafka. And you'll come across many of these open source frameworks and toolkits throughout the day-to-day. Many of them will be presented to you. These are just 3 of the ones that Kate and I have come into contact with and sort of utilized before that have connectors to Kafka that you can utilize when you're building that reactive Kafka system. So we'll take a look at some of them. So if you're utilizing Akka, for example, and you want to connect into Kafka, then you'll want to be looking at the Alpakka library, and within that, the Alpakka Kafka connector API. If you've not come across Akka before, Akka is based on the actor-based framework, so it's a slightly different paradigm to some of the other microservice-based reactive frameworks. And it utilizes sort of a hierarchy system and has mailboxes in order to asynchronously send messages between them. but this is the important Kafka connector you'll need if you're basing your application, your reactive application on Akka and you want to connect into Kafka. What about microprofile? So if you've not come across microprofile before, it's a community-driven specification designed for sort of the enterprise Java microservice community. You can see here that there's some standalone projects as well as the standard specifications that come as part of the microprofile stack. The one we're interested in is Reactive Messaging 1.0. Now, reactive messaging within microprofile works using annotations. So what it does is it annotates an application's beans methods and it connects those annotations, so at incoming and at outgoing annotations, using something called channels. Now, a channel is literally just an opaque string. That channel can be internal or external, and that's where Kafka comes in. Many of the implementations of microprofile, including our open source implementation from IBM, which is Open-Liberty, come with their own Kafka connectors, their own implementation of it. And that sort of channel, that connector is how you connect microprofile reactive applications with Kafka within your own application. And then we've got our last sort of framework we're going to be taking a look at, which is Eclipse Vert.x. So Eclipse Vert.x, you might have seen already in Clement's talk, is a polyglot toolkit. It's based on the reactor pattern. It's non-blocking, event-driven, and it includes this distributed event bus, which really allows us to place sort of that event-driven architecture right at the heart of our application. Vert.x also has a connector into Kafka, and it's actually the framework that we chose to use when we were re-architecturing our own Kafka demo application into a reactive Kafka demo application. So Kate's going to show you a bit of that quickly now.
Yes, so actually the reason this talk came about is because I've been writing Kafka applications and got chatting to Grace about reactive, and we thought, well, why shouldn't we take an existing application and move it to more a reactive programming system? And then what advantages would we get from using reactive programming frameworks like Vert.x as part of that application? So the application that we developed is a Vert.x based application, and it produces to Kafka and then consumes the message straight back again. Obviously, in a real scenario, you wouldn't necessarily do this, but it's a really great tool for just checking, have I configured my Kafka correctly, and have I configured my application with the right security and things like that. We also added a UI because we wanted to help people to get an understanding of what's flowing through their system. So you can see things like the offsets, the partitions, the size of your messages as they're flowing through your Kafka. All of this code is on GitHub, so if you want to try it out and have a look at the actual Vert.x code that we've written and try out the demo, then feel free. But one of the things that we found when writing this demo was it was actually really useful moving to a reactive-based system. So I did have a previous version of this application that just used the standard Kafka client. But one of the things we really wanted was to have a UI for you to start producing and start consuming, but then for you to be able to stop consuming, stop producing, maybe change the message, send some more messages, and really control the lifecycle from this UI. And I did manage to do that using the standard Java Kafka clients, but it was really tricky. And I found I was having to do a lot of working with different threads and sort of setting different things off, and it really wasn't straightforward at all. And then when we started talking about reactive, we realized actually using reactive programming methods were a perfect fit for interacting in this system. And actually, I think there are a lot of Kafka applications that are a perfect fit for reactive programming, but maybe people just haven't realized it yet. So what do I mean when making this change? How has this affected our application? Well, this is the standard setup that you would normally have for a Java Kafka client. And we have this poll loop. So what you have to do with Kafka is you call poll and that gets back a set of records and you loop over all of the records, process them in some ways. So for us, that's sending it back along the WebSocket to the UI. This isn't a reactive programming flow. We're not responding to a set of records, we're actively polling. What frameworks like Vert.x allow you to do is to set up a handler instead. So here we've passed off the task of doing the polling to the underlying Vert.x client, and we just provide a handler that gets called every time a new record comes in. This allows you to build your applications in a much more reactive way. your code is literally reacting to the stream of events that is coming in. And by building a system in this way, it meant that I didn't have to deal with all the threads and having to break out of that polling loop when I wanted to stop receiving new records. Instead, I could make much better use of the resume and the pause. So these are available as part of the standard Java Kafka client, but they're more difficult to access if you're not already using a reactive programming language and writing your application using reactive programming. So if you want to know a little bit more about the changes that we made from the original application to this more reactive and Vert.x-based application, then we have a blog post that you can check out to see all the details and also some of the great other features that we were able to make use of when we moved across to using the Vert.x framework.
So in summary, hopefully what we've shown you through our application and through this presentation is that taking a non-reactive application and just shoving in something like an event-driven backbone or event-driven tools like Kafka doesn't just make your application magically reactive. That's why reactive sort of principles and reactive systems are so important to consider. And to create a reactive Kafka-based application and system, we need to carefully consider the Kafka configurations we've got in order to make the best and the most reactive system possible. But as we said, the open source community is on hand, and there are lots of open source frameworks and toolkits you can utilize with connectors to Kafka to make your application truly reactive and based with Kafka. So if you want to get hands-on with some of these APIs and specifications, check out our online modules here. They're based on an online environment, so you don't have to have any prerequisites, and they're using the microprofile based reactive messaging specification, and they're actually using a Kafka-based application. So really useful if you want to get hands-on with that. If you want to check out sort of a short ebook, Jeremy mentioned it earlier, I've written a short ebook sort of summarizing what reactive systems are, when you'd want to use them, and sort of how to go about using them. It's free and it's online, and the link is here if you'd like to check that out as a reference.
And finally, we have a set of different resources for you to get started. So some reactive resources, all of the reactive Kafka libraries that we've talked about today, and also some links for getting started with Kafka. So if you want to just run it locally on your laptop, check out the quick start guide. And if you want to run it as part of Kubernetes using an operator, then the open source operator Strimzi is a great place to start. And finally, if you are interested in a fully supported Kafka offering, then do feel free to check out Event Streams, which is the product that I work on. So with that, thank you very much for having us, and we'd love to take some questions.